In this example, we're going to look at a combination of a compound parabolic concentrator, or CPC, used to minimize the angular distribution of light coming from an LED. In this particular case, we have a commercial LED in our model, and we've got very accurate representation of this LED, the physical geometry, going into this CPC, and then we're going to take the light distribution from the LED and look at its pattern on this surface at some distance. So let's take a look at the results of the analysis. Just bring up a ray trace, and we can see the light coming in, and some of the light is going to hit the CPC, some of the light is going to come directly from the LED to the detector surface. And I'm going to zoom in a little bit, and we can see some of the ray paths, and again we see that a lot of the light does go straight out, missing the reflector, and some of the rays strike the reflector multiple times before they exit out of the system, and then some rays might just reflect once as they head out. The idea is this particular CPC has been designed to accept this LED at its base end, its smaller end, and what we want to do is send the light out at an angle of incidence no greater than 30 degrees. So we're going to take light that's coming at plus or minus 90 degrees from this LED and then have light coming out only in an angular range of plus and minus 30 degrees at the output face. So let's take a look at some of the analysis. The first thing I'm going to do is look at an irradiance distribution on our detector surface, and let's take a look right here. And this is showing the intensity distribution, and we can see we have an energy concentration towards the center, and it falls off as we go out. Because of the number of rays I've traced and the pixelization on my detector, it's a little bit noisy. So what we've done is applied a simple statistical averaging to take care of shot noise effects. And this is what that looks like after this simple averaging. And again, we get the same type of information, but it's a little bit more understandable with the noise removed. The other information we want to look at is the angular information. So now this is looking at the intensity in a direction cosine space. For those of us who deal better with angles, this is in an angular space, and we can see we're going from minus 90 to plus 90 degrees. And we can move our cursor around to get an idea of what the angular spread is at different cross sections across our energy distribution. But again, we also see a little bit of noise, so next thing I did was average the data. And this is what the smooth or average data looks like. Again, a simple 1 pixel type averaging. And if we look at a cross section through that distribution, we can clearly see light coming from our CPC matches the required 30 degrees. The next thing we're going to do is take this base CPC and LED and create a close packed array of them. In this particular case, what I've done is I've created a hexagonal array. And what we're going to do is to position an LED at each of these 6 points. So we're going to have 6 CPCs and LEDs surrounding this center. And I just unsuppress my drawing right now. So again, what we see is an array of 7 identical CPCs. And similarly, what I'm going to do is use that same pattern to create the distribution of LEDs. And now what we'll do is look at the results of the analysis. Here we already have the data stored, so let's take a look at the ray trace graphics. And again, each of the CPCs will be having a distribution of energy. Each CPC is designed to have the 30-degree cutoff angle. You can see my detector is a little small to capture all of the rays, but we'll still be able to get good analysis. First thing I want to do is look at a power per area, or an irradiance map of the surface. And here's an initial pattern, and you can see the results of each of the CPCs. There's still some separation of the energies, and even with averaging, we still see those results. Obviously, as we moved our detector in and out, that separation will increase or decrease. But most important is what is the angular distribution. And here is a false color picture of it, and we can clearly see the cutoff in this area. But it's much simpler to look at it as a simple distribution section. And again, with all of the CPCs with the array, we still have the 30-degree cutoff. And what's interesting, of course, is how does the array compare to the single unit? And as you can see, other than the maximum intensity level, the distributions, as expected, are virtually identical because we have similar systems. We just have more energy when we have multiple LEDs. The other thing to mention, the CPC is an equation-driven surface. So in this particular case, I've defined a CPC for a 3 millimeter input radius and a 30-degree output cone. If I need a system to use a different sized LED, so a different input aperture size, or if I want a different angle of output energy, all I need to do is go in and modify the equation-driven CPC definition, and I have my new CPC. I do not need to go and create new geometry every time I want to use a CPC in a design. I simply have a CPC geometry stored on my computer, and I reuse it anytime, taking clear advantage of the document reuse capabilities of the SOLIDWORKS engine.